Hi everybody, this is Dr. Nigro with a Chem calculation screencast. This screencast is going to cover the common ion effect. Now, before you can get into the common ion effect, you have to understand solubility product constants, KSP, how to calculate them, how to write the expression. If you do not understand that concept at this time, please go back and watch the screencast that focuses on KSP and its uses. Once you have that information and those skills built, then come back to this one. All right, so let's talk about the common ion effect. All right, so the common ion effect describes the effect of an ion already present in solution on the solubility of an ionic solid. All right, it's really an example of Le Chatelier's principle. All right, so if you haven't looked at Le Chatelier's principle, that also would be a good idea. All right, Le Chatelier's principle is a principle that states that if you stress a system at equilibrium, then the system is going to respond to that stress in a way to decrease the effect of that stress. And the common ion effect is an example of a system trying to decrease the effect of having a common ion already present in solution when you try to dissolve something. All right, so when you prepare a solution, you have a couple choices for that solvent. All right, you could use pure water. All right, and if you do that, there should be no other ions present in that water, so the common ion effect will not occur. All right, or you could use some sort of ionic solution, and let's say that in that ionic solution you have chloride ions and sodium ions. All right, if you then try to dissolve something that has one of those two ions in it, it's going to be more difficult for that solid to dissolve because there's already some of that substance present, and the equilibrium is going to be such that it's going to want to shift. That equilibrium is going to want to use up those ions and reform the solid. So your solubility, you're going to see a decrease. All right, so you have a choice. All right, and we're going to look at those calculations for both. All right, but in the end, if an ion is already present in solution, that is in common with the ions in your solid, then solubility will decrease. All right, and the reason for this is that when you run your calculations, you're going to find that your reaction quotient is going to be greater than your KSP value. All right, and so because of that, less solid will dissolve. All right, if you want to think of it this way, by having a common ion already in solution and then trying to dissolve a solid that has that ion in common, it's basically supersaturated your solution for that particular ion. All right, and if either ion is supersaturated, then you consider the whole solution supersaturated. So you're going to be much more likely to have a precipitation event occur. All right, and then just in general, whenever you have a common ion present, your solubility is going to decrease. All right, now this is most important for our less soluble ionic solids. All right, if you try to dissolve NaCl, it's going to dissolve until you reach the saturation limit. All right, common ions aren't really going to impact our already very soluble salts, but those less soluble salts are going to be heavily dependent on the presence of this common ion, their solubility. All right. Okay, so we're going to try a couple of these problems. Now, to do these problems, you have to have the ability to do Rice charts. You need to know what KSP is. So if you don't understand either of those concepts and these problems seem difficult, please go back and watch those screencasts. That will help immensely. And then you can come back. All right, so we're going to calculate the solubility of iron 2 hydroxide in pure water and in 0.001 molar NaOH. All right, we are going to have a KSP value of 1.85 times 10 to the negative 14. So you can see based on that KSP value that iron 2 salt hydroxide is not particularly soluble. All right, so we're going to start with pure water. All right, so I'm going to write out my dissolution reaction. So I've got solid iron 2 sulfate. It's going to dissolve into iron plus 2 ions, and I'll get 2 hydroxides. All right, so ICE. So again, initially excess solid doesn't dissolve very well, so it's going to be a ton of solid around. None of these 2 ions because it's in pure water. All right, we'll lose some of the solid and gain some of the ions, 2x for that hydroxide. The solid will still be in excess at the end, and we'll have a certain amount of each of those ions. All right, so our KSP expression, Fe plus 2 times OH minus squared. All right, so we use that KSP value, 1.85 times 10 to the negative 14th, x times 2x squared. So we're going to end up with 4x cubed. All right, then we're going to divide both sides by 4 and then take that cube root. We're going to find that x is equal to 1.67 times 10 to the negative 5th molar. All right, and that's going to equal the concentration of the ions, and then 2x is going to be 3.33 times 10 to the negative 5th molar, and that's going to be the amount of hydroxide ions that are present. All right, so that's in pure water. All right, now we're going to put it into 0.0010 molar NaOH solution. All right, so again, the dissolving Fe plus 2 aqueous and 2 OH minus aqueous. All right, follow the same ice chart. Excess for the solid, 0 iron, but because we're in this sodium hydroxide, we do have a source of hydroxide ions already present. So we need to include those in our initial line of our Rice chart. All right, so in NaOH, it's a 1-to-1 ratio from the NaOH to the OH minus. So that means I have a concentration of 0.0010 molar hydroxide initially. All right, then we have the change minus x plus 2x, and then in the end, excess for that iron hydroxide, x for the iron ions, and then 0.0010 plus 2x for the hydroxide ions. Okay, we're again going to do KSP. It's going to look exactly the same as we did with our pure water. Don't forget your square for your hydroxide. And then we plug in 1.85 times 10 to the negative 14th. It's going to be x times 0.0010 plus 2x squared. All right, now this could get very messy mathematically. All right, but we can make an assumption here. We can use our 5% rule. All right, that KSP value is very small. So that means that the amount that's actually going to form ions is probably very small. So in comparison to 0.001, that 2x value is probably going to be so small that it's almost irrelevant. All right, so we're going to assume that this doesn't matter. All right, and that's going to simplify our math for us. All right, so we end up with 1.85 times 10 to the negative 14th is equal to x times 1 times 10 to the negative 6. That's that 0.001 squared. All right, we divide that over, and we find that x is going to be equal to 1.85 times 10 to the negative 8 molar, and that is the concentration of iron plus 2 in solution. All right. If I were to take this value, double it, and then add it to 0.001, we find that the concentration of hydroxide is basically still 0.001 molar. All right. So again, nearly irrelevant. If you want to check, all right, take your answer, 1.85 times 10 to the negative 8, double it, and then divide it by the 0.001, multiply it by 100, and you'll find that you are much, much lower than 5%. So your assumption is valid here. All right, but what I want to look at here is the iron concentration in pure water versus in this solution with the hydroxide present. You can see that we have decreased the amount of iron present by a factor of 3. I mean, there is so much less present, and that is because of the presence of that hydroxide ion. That common ion effect causes the system to be stressed because it's already got one of the ions present that iron 2 hydroxide is trying to split into. And because of that, the system does not want to allow more hydroxide into the aqueous solution. So it tends to decrease the solubility of everything that is present. Okay, let's try another one. How many moles of silver chromate will dissolve in 1 liter of 0.1 molar silver nitrate? And then the KSP for our silver chromate is 1.12 times 10 to the negative 12. All right, so this is going to be very similar to calculation to what we did for the second part of number 1. All right, so we're going to start with our reaction. AgCrO4 solid splits into 2 silver ions plus 1 chromate ion. All right, we're going to set up our ice chart. All right, again, excess for our solid. All right, now we're dissolving it not in pure water, but silver nitrate. So that means we do have silver ions present. All right, we have 0.1 molar silver nitrate, and it's a 1-to-1 ratio for the silver nitrate and the silver ions. So that means we have 0.1 molar silver ions already present, and then no chromate. Lose some of our solid, gain some silver ions, gain some chromate ions, and in the end, at equilibrium, the solid is still in excess. We'll have 0.10 plus 2x for the silver ions, and then x for the chromate ions. All right, we'll write our KSP expression. It's going to be silver ions squared, and then our chromate ions. Plug in our KSP value, 1.12 times 10 to the negative 12. All right, so we're going to have 0.10 plus 2x squared times x. All right, now similar to the problem above, we need to think about whether the amount of ions that are going to be produced in this process are meaningful compared to that 0.1 value. The answer is going to be no. All right, we have 1.12 times 10 to the negative 12 for that KSP equilibrium constant, which means not very much is going to dissolve. All right, so we're going to make the assumption that this 2x does not matter. Okay, so we end up with 1.12 times 10 to the negative 12. We'll square that 0.1, and we get 1 times 10 to the negative 4th times x. All right, divide both sides by 1 times 10 to the negative 4th, and we find that x is going to be equal to 1.12 times 10 to the negative 8th molar. All right, again, if you want to check, let me do this off to the side just so you can see it once. If you want to check if your assumption is okay, here's how, well, I'll do it over here. I have some room. All right, I'm going to take what I ended up getting. So it's going to be 2 times 1.12 times 10 to the negative 8 divided by the number that I assumed it was so much less than, and then I'm going to multiply it by 100%. And if this value is less than 5%, then my assumption is valid. All right, so 2 times 1.12 to the negative 8 divided by 0.1 times 100. It's a very, very small number. Hold on, my calculator. -8 divided by 0.1 times 100. Yes. Okay. So it's 2.24 times 10 to the negative fifth percent. All right. Which is much less than 5%. So we are okay. All right. Now let's go back over here. All right. It wanted to know how many moles of this Ag2CrO4 are going to dissolve. All right. So this X, this 1.12, all right, this is going to be equal to the concentration of CrO4 minus 2. All right. But this is also equal to, which is equal to the concentration or the amount, maybe amount might be a ritter, of Ag2CrO4 that dissolved. All right. But we want that answer in moles. All right, so we need to take our value, 1.12 times 10 to the negative 8 moles per 1 liter, and then we're going to multiply it by the volume, which in this case is 1 liter. So that's going to cancel. We'll be left with moles. So 1.12 times 10 to the negative 8 moles of that AgCrO4 dissolved. All right, now if it had asked for grams, we could have used the molar mass, calculated the grams. All right, but this is how we determine how much actually dissolved. Now, if we'd been in pure water, this number would have been higher because we would not have had the common ion effect, so we would have seen a higher solubility for our solid. All right, let's try this last one. How many grams of NaF must be added to 1 liter of a barium fluoride solution to reduce the molar solubility? Keep hitting the wrong thing. To 6.8 times 10 to the negative fourth molar. The KSP for this particular salt is 1.8 times 10 to the negative 7. All right, so I'm going to start again with my reaction. So I've got barium fluoride. Split that into barium plus 2 ions and fluoride ions. All right, now if we think about it in terms of a nice chart, all right, so we're going to have excess barium fluoride. All right, we are not going to have any barium ions initially. All right, but we are going to have some amount of fluoride ions. Let's not give it, I'm going to call it Z. All right, that's going to come from that sodium fluoride, and that's where we want to get. That's the number we're looking for, because if we know how many ions we need to have present, I can use that to figure out how many grams of that salt I need to prepare to dissolve. All right, the change is going to be the same. We're going to lose some of that solid. We're going to form some of the ions, and then we're going to end up with excess solid, some amount of barium, and then Z plus this additional amount of fluoride because of the dissolving process. All right, now we want to reduce the molar solubility to this value. All right, so that means I want to have 6.8 times 10 to the negative fourth molar as the change. All right, so this value is X. So down here, 6.8 times 10 to the negative fourth molar. And then here it's going to be Z plus 2 times 6.8 times 10 to the negative fourth molar. That is the molar solubility. That's the amount that can dissolve. All right. So we end up at equilibrium with 6.8 times 10 to the negative fourth molar. Z plus 2 times 6.8 times 10 to the negative fourth. So what is that? 6.8. 1.36 times 10 to the negative third molar. All right. So then I'm going to take those two values and I'm going to plug them into my KSP expression. And you'll see I have an unknown, but only one, Z. All right. So KSP is going to equal the concentration of barium times the concentration of fluoride squared. Our KSP value here is 1.8 times 10 to the negative 7th, and that is going to be equal to 6.8 times 10 to the negative 4th for the barium ions, and then Z plus 1.36 times 10 to the negative 3rd squared. All right, now mathematically, I'm going to divide that 6.8 times 10 to the negative 4th over, and then I'm going to take the square root of both sides so I don't have to do a polynomial because I don't like them. But if you want to do a polynomial, you do you. I'm going to do me. So I'm going to divide that 1.6 over. So 1.8 times 10 to the negative 7th divided by 6.8 times 10 to the negative 4th. So I'm going to get 2.65 times 10 to the negative 4th. That's going to equal to Z plus 1.36 times 10 to the negative 3rd squared. Square root of both sides. It's going to give me 0.0163 over here. Z plus 1.36 times 10 to the negative 3rd. So I'm going to need to subtract 1.36 times 10 to the negative 3rd from both sides. And I'm going to find that Z is equal to 0.0149 molar. All right, so that means when I start, I need to initially have this amount of fluoride ions present. All right, and that amount is coming from that NaF. All right, so I'm making 1 liter of NaF solution. All right, and I need, whoops, my number in here, 0.0149 moles of F minus for every 1 liter. So let me change this. This unit should actually be F minus. All right, so that's going to let me cancel my liters. All right, and according to the formula, 1 mole for every 1 mole. So it's a 1-to-1 ratio. It's going to get rid of my moles of fluoride. And then for my last step, 1 mole of NaF, I need to go to grams, so that needs molar mass. So I look it up on the periodic table, add them up, 41.99 grams. It's going to cancel the moles, so I'm left with grams of NaF. And I find that I need 0.63 grams of NaF. That's how much I need to dissolve into 1 liter. That will then give me the 0.0149 moles of fluoride ions initially. And then when I try to dissolve my barium fluoride, it will keep that solubility at that 6.8 times 10 to the negative 4th molar level. All right. So you can see that problem was a little bit more complicated. All right. But all skills that you should be able to do. You could do ice charts. You know what we mean by molar solubility. You can write a KSP expression and solve for that unknown. And then your understanding of formulas and molarity lets you work your way back to those grams. Okay? So again, the common ion effect just describes the effect of having an ion already present in solution that is in common with one of the ions you're trying to dissolve, or one of the ions that's already present in the solid you are trying to dissolve. All right, the common ion effect always leads to a decrease in solubility of your particular solid because of Le Chatelier's principle.